Today we are starting a new topic, the electrostatic phenomena. Then in today's lecture there are a few things that we will be discussing about electrostatic and what's electrostatic, what is a positive charge, what is a negative charge, and so on and so forth. Okay. So the first thing is, like, in general, materials can be categorized as conductors and insulators. Then an electrical conductor is a material that has a freely moving electrons, okay, and it can conduct electricity very easily. On the other hand, an insulator is a material which charges cannot move freely, okay. Most of the time, like, charged particles are very much close to the material or to the atoms, okay. Those are the few examples that you can cite. Conductors, most of the time metals are good conductors. They can let electric charges move freely, and the result, they are a good electric conductors. They let electric flow through them. Whereas insulators are materials in which charged particles don't move that much freely. Good examples are glass, rubber, and so on and so forth. There are, like, atomic details that you can talk about, like why why conductors have, like, freely moving charged particles, whereas insulators don't have that much of, like, freely moving charged particles. That's, like, it can be detailed later when we talk about, like, atomic structure. Most of the time, like, conductors, they have, like, at their outermost shell, like, they have electrons from 1 to 3 that can easily be, lost to other materials, and those outer shell electrons move freely around. Whereas insulators, most of the time, they don't have, like, those like outer shell freely moving or transitioning electrons on them. So we're going to come and define what those electrons and those protons are in a few. So something that I'm also would like to ask you, like, before we go further down into the topic. So, like, for instance, what are charged particles and so on and so forth. Like, for instance, I'm sure that, like, you might have noticed, like, if you rub a rubber material, let's say, and then you rub a rubber material, and you have that rubber material, it's nicely rubbed, like, let's say you wrap it, like, with a fur. Most of the time, like, for experiment, like, what we use is rubber. It's a rubber material, and then you rub it with cat fur. That same simple example works with your comb, okay. So, for instance, like, if you rub it, and for some reason, then let's assume that, like, this is just a small piece of material, or it can be paper. Mostly we use papers, or some kind of small ball of foam, okay. Then if you bring this close to this object, what will happen is, like, there will be an attraction, right? The paper or the small foam material will be attracted. But you may wonder, like, well, this is an insulator. This is an insulator as well. And those materials, you are bringing them close to each other, and then what's happening? So according to Benjamin Franklin, what he said is like, you know, when he conducted such kind of experiment long time ago, then eventually what he said is like in every material, pretty much in every material, there are particles. We call them charged particles. And those charged particles in general, they are positive and negative. Okay. Then those charged particles, then if you bring them close to each other, then what will happen is like they attract to each other like a magnet. Sometimes they attract to each other, sometimes they repel each other. So what in general happens is like when you, so as we said, like you have an insulator and an insulator, and then but one is really very well wrapped, like, you know, against a fur material, and then when you bring it to another material which was, you know, pretty much like neutral, then there will be an attraction. So according to Benjamin Franklin, what he said is like in every material, whether it's a conductor or an insulator, there are things that we call them charged particles, positive and negative charged particles. And that's because of those presence of those positive and negative charged particles, those objects like to attract to each other. So what is happening is like if you have the rubber, right? So without being rubbed, so then if it's not really rubbed against a cat fur or something like that, what will happen is like it has equal number of positive and negative charges. Okay, equal number of positive and negative charges. And likewise, like, you know, the small foam that we were talking about, like, then that one has also equal number of positive and negative charges. Yeah. Okay, those are mostly like in a small kind of material, we call them like atoms. Okay, so now, but when you wrap this this thing like with let's say with a cat fur, what would happen is like it's going to gain some extra electrons. Okay, it's going to gain some extra electrons in it. Okay, then when you bring it close to this guy, what will happen is like, so in principle, like charges repel each other. Okay, so like charges repel each other. Unlike charges attract each other. Now, when you bring this negatively charged, so what's happening is like some of the negatively charged particles from the fur will jump into the rubber rod, and then it's going to make it a negative charged object. Then when you bring it close to this small foam or paper, what would happen is like, you know, I mean, you can have an exaggerated version of it. Like what will happen is like all the electrons wants to run away from this object. Okay, wants to run away from the negatively charged rubber. So if I try to have it like in a little bit exaggerated kind of diagram, so you have this guy and it's like negatively charged pretty much. Okay, then the other object, so you know, like, so the building blocks of materials, this is also an exaggerated version of it, so they have atoms inside, and then those atoms, like in a conductor, the charged particles, they are not really freely to move, but they can shuffle around within their space. That means, like, you know, in every atom there's a positive and a negative one. Like, you know, you can imagine those are atoms, right? same thing, like pretty much in every material. I mean, this is just an exaggerated version of it. Then what will happen is, like, because of this negative repels negative, then what will happen is, like, within the atom, the negative charges will move away and the positive charges will come on this side. See? They are creating some kind of like a south pole and then a south pole, north pole, and a magnet or something like so. Then they create some kind of, you know, polarization, you may call it, like they will be polarized. Then you see, now all the positives are like on one side. You see, all the positives are on this side. And then what will happen is, like, negatives was positive, then there will be some kind of attraction between them. So there will be an attraction force or attractive force being developed in here. Okay, so that's what Benjamin Franklin, eventually investigated, like why those things are happening, and then eventually he found out and learned that, like, in every material, like, there are positive and negative charges, and then sometimes, like, when you rub one object against the other, there will be a chance that, like, some of the charged particles can jump from one to another one, making one like either positively or negatively charged. Okay, so likewise, like if you rub a glass rod with a silk material, what's going to happen is, like, the glass rod will let some of its negatively charged particles to jump on the silk, and it becomes a positively charged object itself. Okay, so in general, like, so that's why, like, you see those kind of attractions. So in general, just keep in mind that, like, there are positively charged and negatively charged objects inside every object. Okay, so that's why, like, for instance, you know, on a dry winter day, when you are at home, for instance, what you can try is, like, you know, rub your feet on the carpet. You know, it's just like walk on the carpet in such a way that, like, you are sweeping with your feet, and then if you go and then, like, touch a knob, a doorknob, which is mostly a metallic material, then what will happen is, like, you will feel an electrostatic shock, right? So you know why that is happening? That is happening because of the electron or the negatively charged particles or something, the extra that you get from the carpet. They want to discharge themselves and then, you know, run away from your body, and they were looking for an outlet. Then as soon as you touch the metallic material, you know, they flash out of your body, and then, like, with a huge number, and then you feel that shock. Okay, so having said that, those positive and negative charged particles later named as electrons and protons. Okay, so everything that we say from now on, like positively charged particle, is a proton. So those positively charged particles are called protons. Okay, then likewise, the negatively charged particles are known as electrons. The negatively electrons. Okay, electrons, very good. Now we already mentioned that like charges attract each other, and like charges, like, repel each other. So let's go ahead and then, like, try to answer this example or this question. The question says, like, the diagram below showed the uniformly charged spheres the charge on the right sphere is 2 times as large as the charge on the left sphere, which force diagram best represents the magnitude and direction. So now the question is, like, pretty much you have those spheres, and then this is positively charged, this is positively charged. The arrow represents the forces, and you may call this force 1 and you may call this force 2, and the size of the arrow represents, like, how big the force is. So it means, like, you can see that, like, the longer arrow means like larger force and smaller arrow means smaller force. So if you bring those two charged particles close to each other, which diagram do you think is a well representation of what is happening, the two objects? Like, we already mentioned that, like, there is an attraction or repulsion force between charged objects, and then in this case you have two positively charged objects. One has a charge of, let's say, 2 and quote unquote, and the other one has a charge of like 6 positive charges. So if you bring them close to each other, the first thing that you will notice is, like, the two objects will repel each other. Okay, they repel each other, and then if they repel each other, most people may say, like, oh, this one, because it has a smaller side, then it's going to experience a smaller force, and this one being a larger charge, but it's going to experience a larger force. I don't know about that. Then number 1 says, like, oh, well, this one, the small one, will experience a force in this direction, and the other one will experience a force in this direction. By the look of those diagrams, the first thing that you need to look for is, like, which force diagrams represent repulsion, because we're expecting repulsion. So this represents repulsion, this represents repulsion, then this one. And now, out of those 3, which one do you think will make sense? Always keep in mind that, like, something that you learned before, it's just like it becomes valid all the time you move forward in other chapters. So in Newton's laws of motion, something that we mentioned, for every action there is an equal but opposite reaction, and that principle or that law is still applicable here as well. That means, like, if one positively charged object pushes the other with 10 newtons of force, then it experiences 10 newtons of force back, or vice versa. So there is like, what you need to look for is, like, which one represents, like, equal side of forces. Like, the amount of force that object 1 applies on object 2 is the same as the amount of force that object 2 experiences from object 1, only that in opposite direction in this case. Why? Because both are positively charged. So therefore the answer is choice 4. Okay, choice 4. Now the next thing is, like, what we were mentioning, like I was giving you a note earlier, like, what is happening is, like, so okay, there are objects can be positively charged, objects can be negatively charged. Okay, but most of the time, if they are by themselves and you let them sit, then objects are neutral. Neutral means the number of electrons and the number of protons in that object are the same. Okay, now the question is, now, how do we normally charge objects then? How do we make one object positively charged? How do we make another object positively charged? The first way is by conduction. Okay, by conduction. By conduction means, like, you can charge an object by direct contact. You let an object and it's just like touch the other object, and then, so I was trying to mention earlier if you remember, if you rub let's say a glass material, or if you rub like a rubber with a cat fur, or it's just like, you may also use like regular cat fur, what's going to happen is the following. So let's say, just to make our life a little easier, so let's rub again rubber material with fur. Then this is going to have like negative charges. Those are the negative charges. Okay, those little things, I'm representing them as negative. Then now, if you take like a metallic cylinder object, so this metallic cylinder object, not cylinder, spherical metallic object. Mostly we prefer metal for the experiment, just to show, because in a metallic object, like negative charged or negative charged particles, they're freely to move. They're mostly like, they wander around freely. That's why the metallic materials are conductors. So what will happen is, like, if you bring those negatively charged object close to this object, what will happen is, like, all the negative charged, since they are freely moving, they are going to come to the other side, leaving their positive counterparts. Okay. In a neutral, like, you will have within the atom, you will have equal number of positives and negatives. Okay. But otherwise, like, what will happen is, like, unlike the insulator, like in the previous example, if it is an insulator, like, electrons they're not really freely to move around, and then they don't just go and populate on this side. They don't do that. Like, mostly they just simply form some kind of what we call is like a dipole. It's just like only polarization. One side of the insulator will be a little bit positively charged, and the other side is a little bit negatively charged. But unlike that, like in a metallic material, the electrons run away freely because they wander around freely, and then they become like on that side. They just jump in that side. Okay. So as a result, like, you're going to have that. So when you bring it close to that, but what if you touch the metal with this negatively charged, and then if you touch it, okay, what will happen is, like, those negative charged particles from the rubber, right, they're very excited, and then they can jump and then come to the metallic material. What will happen when that happens? That metallic material will have extra negative charge. Then you will charge it like negatively. So now the metallic material is negatively charged. Okay, negatively charged. Then that kind of charging an object by touching it is known as by conduction. Okay. Then the other type of sorry, I'm trying to move this guy. So the other type of charging an object is known as by induction. Okay. So, don't need those ones. Let me clear up this. Okay, by induction. So by induction, it means, like, without touching the the previous metallic material, without touching it directly with the rubber. So this is what's going to happen. So there is no touch. Like, you still have, like, the rubber material, which is rubber rod, which is negatively charged, and then you have this metallic material, and you bring it close to this. As always, what will happen is the positives will populate on this side. Okay, why? Because their counterparts, the freely moving negatively charged particles, will run away to the other side. Okay. Now, what will happen is, like here, there is no touch. And in the previous, you don't touch this object with the charged particle. Okay. So, but rather what will happen is, like, touch this with your finger on this side. What will happen? What will happen is, like, those electrons will jump to your body. They were looking for an escape anyway. They will jump into your body because, you know, you are a human being. Humans mostly, we conduct electricity, and then those charges normally they will jump to your finger. What happens is, like, they will leave the metallic object positively charged. Okay. So those are, you know, jump. The electrons jump from the metallic sphere to your finger and to your body. You know, humans, like, and in general the Earth also, we're you know, you may consider yourself like a reservoir of tiny reservoir of electrons, you know, or charged particles. All the negative charges, like, they jump into your body. You know, to some extent, you might not feel it, but sometimes you feel it as an electrostatic shock, right? So when that happens, now your metal is positively charged. And that's by induction, because you didn't touch him. You know, you didn't touch him. In essence, you didn't touch him with the negatively charged rubber. Okay. So now those are the two different types or ways, like, we charge an object. Okay. So the next item that we are very much interested in this topic is known as the electrostatic force. So we were saying, like, you bring two charged objects or two charged particles close to each other, then you end up with you know, you end up with an attraction or repulsion force, depending on, yeah, what you have. So then, how much is that force between those two charged particles? That means, like, you have a charged particle here and you have another charged particle here, and we usually represent the charge of a certain object or particle using Q. Some textbooks use uppercase Q, some textbooks use lowercase q. In our case, likely to use, like, you know, lowercase q. So Q here represents charge, and not change, it's charge. And this a unit of charge is Coulomb. Okay, and it's rated as uppercase C. Okay, uppercase C. Now, and you know, a negatively charged object of course has a negative Q, and a positively charged object has a positive Q. But in this textbook, the way we are going to calculate things is, like, we're just simply take the positive or the absolute value Q's, and then we are going to say, like, either the force is attraction or repulsion, depending on what kind of charged particle you have. Okay, so if those two charged particles are positive, then the force will be repulsion. Okay, so we're not going to spend too much time to use a negative value for negative charge or a positive value for positive charge. No, we're not going to do that. We just simply use always the positive values of the charge, and then we go ahead and then do the calculations. Okay, so then if you look at this equation looks a lot familiar if you pay attention to it. Why? Because if you remember, we learned something, an equation that looks like this. Do you remember it now? Newton's law of universal gravitation, right? Look, you have a force here, you have a force here. You have a constant here, you have a constant here. You have charge here, you have mass 1 here. You have charge 2 here, you have mass 2 here. You have the distance between the two masses, you have the distance between the two charges. Very similar to each other. This is like Newton's second law. It is an inversely proportional to the square of the distance. It's an inverse square of the distance equation. Okay, that means like when the distance doubles, then the force decreases by 4. It means like as the distance increases, the force decreases. That's what inverse relationship means. So Coulomb's equation is like, you know, the distance between the two charges is r. Then the force between them is sometimes represented as Fe, to show that's an electrostatic force, is K into Q1 times Q2 divided by r squared. So it's already written here. And K is known as Coulomb's constant, and it's 9 times 10 to the power of 9 Newton meter squared per Coulomb square. Okay, so I want you to go ahead and then look at like example 12.2. I'm going to solve it here as well from your textbook. So the example reads like this. The example reads: two positive charges, one 2 microcoulomb and the other 7 microcoulomb, are separated by a distance of 20 centimeters. What is the magnitude of the electrostatic force that each charge exerts upon the other? We already mentioned this in that diagram example that I asked you, like the force between the two charges is the same. Okay, it means like because of action and reaction, the amount of force experienced to each other is the same. So in this example, it's a direct example from the textbook. Then, as always, let's list our given parameters. It says Q1 2 microcoulomb, because 1 coulomb of charge is a lot of charge. It is a lot. So usually in the order of microcoulombs that we're going to deal with, and it is 7 microcoulomb. The distance between the two r is 20 centimeters. You need to convert this to meter. It will be 0.2 meter. And on the other hand, keep in mind 2 microcoulomb means 2 times 10 to the power of minus 6 coulomb, right? Likewise, 7 times 10 to the power of negative 6 coulomb. Then now you are asked to determine how much electrostatic force is happening between the two. You just go ahead and then solve your problem by applying the Coulomb's equation. Okay, so according to Coulomb, electrostatic force between two charged particles is K times Q1 Q2 divided by r squared. We needed to convert everything in SI unit because our K value is constant. K is a constant, and it's given as 9 times 10 to the power of 9 Newton meter squared per Coulomb square. Everything is in SI unit in here, like their SI units means like their basic SI unit. So 9 times 10 to the power of 9 Newton meter squared per Coulomb squared, multiplied by, you have this law like this, Q1 which is 2 times 10 to the power of -6 Coulomb, and Q2 just 7 times 10 to the power of -6. Divide that by 0.2 squared. If you put in like the denominators properly, you can do unit elimination. One column eliminates another column, and this column eliminates this column. And here you have, of course, a meter square. Okay, that meter square cancels out with this meter square. Then you are left with 1 unit, which is Newton. That's it. So if you do that, then what you're going to get is, it will be 0.126 Newton divided by 0.2 squared is 0.04, right? So therefore, if you do this and simplify it, your force is going to be 3.15 Newton. Okay. All right. So, you know, it's just like the equation is, it's a basic equation, and then it's very easy and straightforward to apply. Okay. So we can go ahead and then probably solve another example from the textbook. So from the textbook, I want you to try. I'll read it for you, of course. So E5 in your textbook state the following. 2 charged particles exert an electrostatic force of 32 Newton on each other. What will be the magnitude of the force B if the distance between the 2 particles is increased to twice the original distance? So now you don't need to apply the Coulomb's equation or formula directly, okay? But in this particular case, but it's a conceptual question, which is really a good one. So what it says is like E5. It says like you have 2 charged particles. It's fine, you know, you can assume both are positive. It means they repel each other by a force equivalent to 32 Newton. Okay. Then now it says, what will the magnitude of the force be if the distance between the 2 particles is increased to twice the original distance? Now, the separation between them has increased twice. Then now the new force, I'm going to call it new. Yeah, how much? So look at the equation. This is like, you'll need to answer this by looking at the equation. Like, just simply look at the equation. Force equals K into Q1 over Q2 over R squared. Okay. So if you look at this equation, this is, as we said it, right? Force is proportional to the inverse square. It's not only inverse, the inverse square of the distance between the 2. objects, or between the two charged particles. So you can see that like two forces, when the force, so that means as distance increases, force decreases. Okay, but how does it decrease? As we said, it decreases by the square of the inverse of the distance. So that means it's going to decrease. That means from 32, it's gonna decrease. Decrease means you will have to divide it by the inverse, not by the distance square, but by the inverse of the square. That means doubled, the distance doubled, then therefore you need to double the square and then invert it to get the new force. That is what the new force is. Okay, this is not the case that like when the force doubles, when the distance doubles, the force doubles. No. Or this is not the case that like when the distance doubles, the force decreases by a half. No. This is the case that as the distance increases, the force decreases by the proportion to the inverse square of the distance. Okay? So as a result, like now you will have 32 Newton or 1/4. That's your new force. Okay, as a result, your new force is 32/4, which is 8 Newton. All right. Okay. So this is something that really you need to keep in mind. Okay. All right. So this is, or we already said this. So Coulomb's law, it's an electrostatic force experienced between two forces. It's inversely proportional to the square of the distance between the two particles. Okay. But of course, it's proportional to the charged particles. That means as the charge increases, the force increases. But as the distance decreases, the force decreases. Okay, so this is another explanation, or it's the same equation that we already solved. Okay, so another example. Let's go ahead and solve this example that we see on this slide. So this example states that an alpha particle charge has 2e. Okay, now I'll explain what that 2e means. Is sent at a high speed towards a gold nucleus. So a gold nucleus has 79e. What is the electrical force acting on the alpha particle when the distance between them is 2 times 10 to the power of -14 meter? Okay, so 279. So let's come to our given parameters. Q1 is 2e, Q2 is 79e, and the distance r is 2 times 10 to the power of -14 meter. Let's check. Okay, so now you're asked to find what is the force, the electrostatic force between the two. All right, so E, or lowercase e, sometimes it can be used as the unit of charge. Okay, lowercase e, but that e is like, usually it's E is equivalent to to the charge of an electron. Okay. Or proton. And the charge of an electron equals negative 1.6 times 10 to the power of negative 19 Coulomb. Mirrored here down that you can see it clearly. And I will use another color. The charge of an electron, charge is equal to 1 times 10 to the power of 1.6, not 1. 1.6 times 10 to the power of negative 19 Coulomb. Coulomb is the SI unit, so that's negative. Charge of one proton on the other hand is positive 1.6 times 10 to the power of negative 19 Coulomb. But in this material, or in this textbook, we say that like we are not going to worry, or we're not going to spend much time like when to use negative, when to use positive. We'll just simply use positive, and based on the given charge, like we will decide whether it is repulsion or an attraction. So in our exercise here, what we need to do is like, now you have your Q1. Your Q1, you need to change it to coulombs, then it's going to be 1.6 times 10 to the power of negative 19. It's an alpha particle, it's a positively charged particle. Anyway, so Coulomb. Okay, so therefore your Q1 is going to be 3.2 times 10 to the power of negative 19 Coulomb. Your Q2, on the other hand, it is 79 times 10 to the power of, not 10 to the power of 1.6. 1.6 times 10 to the power of negative 19 Coulomb. Remember, this is for E. That's the same as E. So therefore, when you see like E, it means that 1E is equal to 1.6 times 10 to the power of negative 19 Coulomb. All right. Then, if you do calculation, like, well, let me find my calculator. 79 times 1.6 is 126.4 times 10 to the power of negative 19 Coulomb. All right. So now you need to find your force. Force is like K times Q1 times Q2 over R squared. K is 9 times 10 to the power of 9 Newton. What did we say? Meter squared or Coulomb squared. Don't have to worry much the unit. As far as you put all of them consistently in the same category of units, then they eliminate each other anyway. And then if you know that the SI unit of force is Newton, then eventually you will be left with Newton. Okay, so the first Q1 is 3.2 times 10 to the power of negative 19 Coulomb. Then 126.4 times 10 to the power of negative 19 Coulomb. And the distance, 2 times 10 to the power of negative 14 square. Make sure that you square that value. Okay, so if you properly do this in plugging it in your calculator, this is like as a workout for yourself as well. Try it. If you simplify it, then you're going to get 91.6 of Newton of force between the alpha particle and the nucleus of the gold. Okay, so so this is another example that would like to try. So you try it. It's so most of the problems just revolve around like, what is the force? How does the force increase? What if I triple the force? I mean, the distance between the two forces, what will happen to the force? A kind of question. So the next item is the electric field. Then what is an electric field between two charged particles, or an electric field? What do we mean by an electric field? So an electric field is said to exist in a region of space around a charged particle. So you remember, like, for instance, you know, when we talk about like gravity, you know, if this is the Earth or any mass, we like to have Earth as an example because we experience that gravitational field. So as far as you are closer to Earth, right, what will happen? The Earth pulls you down by g, which is equal to approximately 9.8 meters per second squared, right? So as far as you are within the field, but if you go far away from the Earth, deep into space, right, probably Earth's gravity will no longer materialize to you. Why? The Earth's gravity is not going to pull you because you are out of Earth's gravitational field. Okay, so that is what a gravitational field is. That is what a gravitational field is. But what is an electric field then? Then the same concept applies here. As the Earth pulls down anything or any object with mass in its gravitational field, then electric charged particles also either attract or repel another electric charge that is within their electric field. So simple. It's like gravitational field. The only difference here is this. In Earth's case, it's a mass. Mass is involved. That's gravitational field is because of mass. And there is no positive mass and there is no negative mass. But when it comes down to charged particles, sometimes you have a positive charged particle, sometimes you have a negative charged particle. So that means, in what direction is the electric field then? Sometimes the electric field may like to pull you. Sometimes the electric field may want to repel you. Then scientists came up with some kind of a consensus. That consensus was based on a small positive charge. So what they said is like, let's not make any confusion. Let's have a small test charge, and then that test charge is positive. And then they said, like, based on that positive test charge, in what direction it experiences that electric field, then let's designate that's the way the electric field is. Then if you bring a positive test charge close to a positive charge, what will happen? It's going to push it away because like charges, they repel each other. So because of that outward repulsion of this charge, the test charge experiences, then the electric field in a positive charge is outward or points away from that charge. On the other hand, if you bring a test charge, that's again a positive test charge, near or close to a negatively charged object, what will happen? It will be attracted. It's going to experience like the Earth pulls you in. That's why gravitational field is always towards the center of the Earth. In this particular case, if you have a negatively charged object, then its electric field will be inward. That means you can imagine you are this test charge. You are always positively charged. If you are close to a negative charged object, you will be pulled down. If you are close to a positive charge, you will be repelled. So as a result, like electric field around a negatively charged object is towards into the charged object. Okay, so how do we calculate it? Like, then there is a similar pattern to how we calculated G, or G, if you remember, if you know the mass of the Earth, if you know the radius of the Earth, and so on, you can calculate G, right? G as in the Earth's gravitational acceleration, right? Likewise, here you can find the charged electric field, okay, if you know the force. And then electric field is calculated like this. So let's assume that, like, you have an electric charge. Let's say it's a positive big charge, and then there you have, let's call that one Q1, and we want to find the electric field of this positive charge. And then let's have a test charge. That test charge is Q2, and that distance between them is R. Therefore, the force, the electrostatic force between the two, will be like this. Okay, so the blue color represents the test charge. Okay, now the electric field is defined as the following. The electric field of a certain object is equal to E is equivalent to your force divided by the test charge. In our case, that was Q2. The force between the two charges. So to find this guy's field, the same as like the gravitational field, if you remember, like G can be calculated as G times the mass of the Earth divided by where you are located, R squared. Remember? Okay. So if you substitute K, Q1, test charge Q2, divided by R squared for the force, you still have the other R Q2. Then this Q2 will cancel out by this Q2. So therefore, the electric field is calculated as this, you see? So the electric field describes the effect of a charge Q1 on another charge Q2. So this is what I was trying to say, like, so therefore you can find E F over Q2. So if you simplify that, then of course its unit is going to be Newton per Coulomb. You may have it in a clear view. So therefore you can find the electric field as K times Q, the charge, and at any distance. At what distance that object is, whatever distance it may be. So that means, like, if you have a charge, positive or negative, it doesn't matter. If you want to know its electric field at this location, then you just simply go ahead and apply this equation. Okay, K times its charge divided by R squared, and its unit is Newton per Coulomb. Okay, so now this question, the electric field of a point charge. So find the electric field produced by a 1 microcoulomb charge at a distance of 0.75 meter, B at a distance of 1.5 meter. So first, your given parameters. For A, your Q is 1 microcoulomb. Micro means 10 to the power of -6. R is 0.75. K is 9 times 10 to the power of 9. This is directly from your textbook. So then you can finish this. So what's going to happen? So your E is going to be 9 times 10 to the power of 9. I'm going to keep everything SI unit. Then 1 times Coulomb, microcoulomb means 10 to the power of -6, divided by 0.75 squared. That's in meters. So if you simplify this, how much value are you going to get? Yeah, let's do it together. I'm going to use my calculator as well. So it's going to be 9 times 10 to the power of -9. I'm not positive 9. And then that one, then it is, this is what I get. So I want you to verify if this is correct. Okay, so it is 16,000 Newton per Coulomb. Okay, Newton per Coulomb. So how much would be for B? Like when the distance between them is 1.5 squared, you will apply the same approach. 9 times 10 to the power of 9 multiplied by the charge is 1 times 10 to the power of -6 divided by r squared, now is 1.5 squared. Okay, so again I'm going to help here. Then the answer is 4,000 Newton per Coulomb. Keep in mind this is for power B. You know, the equation is the same, the only difference is so how do you draw electric field lines between two objects? There are rules how you are going to draw electric field. Okay, those are the following rules. The electric field vector or is always tangent to the electric field. Okay, then the number also depends on like so the number of line rows or something like that you are going to show on the electric field lines. It must be proportional to the size of the charge, you know. So you may wonder like what do you mean by that? And so it means like this. So if someone asks you to draw an electric charge, okay, thing is not to respond. So an electric charge, you have an electric charge here, positive, and here you have an electric charge, 2 positives. Then if someone asks you like draw the electric field line, let's assume that the electric field strength, they are going to repel in this case. Coming out of this one is, let's say, 2. How many will come out on the other one? It's going to be 4. Okay, why? Because the strength of the electric field lines depend on the charge. That means like, you know, like for instance, Earth's gravity is more than Moon's gravity because Earth has a lot more mass. The same is true here. So when you represent it in terms of drawings, like those two will repel each other, the electric field lines, they will repel each other. And as we defined it, it's outward for a positive charge. So if 2 electric field lines are coming out of a 1 charge, then if you have 2 charge, the charge of a particle is 2, then what would happen? You will have twice as much. Okay. Then never cross electric field lines. Okay, so don't cross one electric field over another electric field. Okay, so this is already said. It's always outward for a negative charge. For a positive charge, it's always inward. This little guy, this little guy, it's the test charge. Okay, so whatever the test charge experiences is in the direction of the electric field line. All right, so force on a positive test charge in the direction of the electric field, that means away from the positive charge, whereas on the other hand, no. Okay, so now if the electric field is to the right, and if you have a positive charge here, in what direction will it experience a force? Right? It is, we said, it's away. It means this little guy is going to experience force in this direction. Okay, yeah, that's it. How about if you have a negative one? It is opposite to the direction of the electric field. It will experience force in this direction. Okay, so any electric field lines, if you bring two opposite charges close to each other, their electric field lines will pretty much, form this kind of direction. It's like two magnets bringing one magnet on this side and another magnet on this side. Sometimes they repel each other if the poles are opposite to each other. They attract each other if the poles are in the same direction. Okay, so that's pretty much it for today. So till next class, that's it for today. Bye.